All right, so I just wanted to do this presentation on parallel power factor correction and also look at the approach when you're not bringing power factor back to or to unity and you're, say, coming to a power factor or looking to correct to a power factor of 0.9 or something like that, and how we approach it. The first thing I would say is, in terms of parallel, essentially I would say it's kind of an easier process to relate to than series, because if you have a purely parallel circuit, you're just adding another capacitive branch in order to make the total net reactive power zero. So you're taking whatever value of QL you have as a reactive power for the inductor, you're subtracting the value of QC from it, and whatever you have left over, you simply have to add another capacitive branch right across the source, because remember, this represents the load as a parallel arrangement. So this would be the load that needs to be corrected, and in that load there's some QL and QC. Subtract the QC from the QL, that gives you a net QL value of which needs to be corrected with another capacitor or branch over here. And it becomes pretty straightforward because you're not working with a different type of connection than what you've been working with already, which involves capacitive current. So one way to look at bringing this to unity or approaching it as unity is that your IC, your capacitive current, your total capacitive current, would have to equal your total inductive current. So you could just determine the current here in the inductor, determine the current in the capacitor. You don't even need to concern yourself with the resistor if you're just coming to unity. And then from there, do your VS times current IL, VS times current IC, compare the two currents, subtract them, and then add that much more capacitive current so the two currents are equal. So hopefully that makes sense. That's a way to approach unity in parallel without even needing to consider the value of real power. You just go directly into your reactive powers, make them equal, make the currents equal, and you're good to go. But we're going to look at an example of where we're going to take this load and we're going to correct it to a 0.9 power factor, and how we do that. So first of all, if we look at the values given there, in order to figure out their currents, which I'm going to do, I'm actually going to figure out their currents first, and then I'm going to speak on how, if you were doing unity, you could just come up with the value there. And then when we're looking at bringing it to 0.9, I'm actually just going to use a VS times the branch current value to give you your values of both real and reactive power. Okay, so first of all, let's just start by determining what the XL value is from that 22 millihenry branch there. So I'm just going to do that now. Okay, so I get 8.29 ohms for XL here. So I'm just going to, I guess, I'll just write it down here. XL for the inductor is 8.29 ohms. Okay, so now we'll move on to the capacitor, and we'll do our XC value for the capacitor. That equals 265.25 ohms. So XC is equal to 265.25 ohms. So there's our reactances. Now we can come up with our currents. Well, our current for our resistor is obviously 12 amps, right? So that means if we list our currents up here, I'm going to say IR is equal to 12 amps. IL, which is going to be our 8.29 ohms. So we're going to take our 120 divided by 8.29, and we get 14.48. So we're going to go 14.48 amps there. And then we're going to do our last one, which is our IC. So that's 120 divided by 265.25. And we get 0.45 IC. We're going to go 0.452. 0.452 452 amps. So that's 452 milliamps. Okay, so what it means then now is if you wanted to determine how much current you needed to add to this circuit in order to balance these currents, well, you just subtract 452 milliamps from this current, so it looks like about 14 amps of current. I'm just roughly 480 milliamps there, 450, so it's roughly 14 amps of current that you need to add as a capacitive branch in order to bring this to unity. So you wouldn't even need to consider IR to do that. You would just come up with balancing those currents, and then you'd have a unity power factor. And of course, you'd have to go through the process of determining the XC value that would give you 14 amps of current, and then turn that into a capacitance value in farads. Okay, but let's look at the example up here where we're going to first of all figure out the actual power triangle and its power factor, and then we're going to look at improving it, not bringing it to unity, but improving it. So what's the first thing we're going to do is come up with our PR value, or our real power. So that'll be found by VS times IR, 12 amps, right? So that's 120 times 12. That's going to be 1440 for our P value, right? So I'm just going to put this in here as 1440 watts, right? And then we'll just realize that was done by a VS times IR, right? And now we can figure out our QL value. So I'm actually going to put my QL value here, and that's going to be 120 times 14.48. So that is 1737.6, and that would be plus J bars, right? So that's our plus J bars of QL. Now I'm going to do my QC. So sorry, I should make this a little bit easier to see. So now I'm going to do my QC, and that's going to be 120 times 0.452, which gives us 54.24 bars. 54.24. Those are minus J bars, right? So now I'm just going to simply add my reactive powers together, and that will be the result of 1737.6 minus 54.24. (1737.6) minus 54.24. That gives us 1683.36, right? So what it means is that our current power triangle is one that has a QL value here, and I realize this isn't to scale. Maybe I can kind of make it a little bit more to scale by shortening this. So 1683.36, so 1683.36 var, and that's a plus J value, as you can see, right? So this is plus J. Now, if we look at this, we can determine our S value here, and we can determine our phase angle or our power factor that results from this power triangle. So let's do that. So we're going to do that by 1440 plus J, 1683.36, right? And now that indicates that we have a 2215.24 VAs at an angle of 49.46 degrees. So here, this is 49.46 degrees, right? Okay, so now what we're doing is we're looking at what we've got for a power factor for that angle, right? So I'm actually just going to pause this and clean it up because we've got those values, and then we'll talk about what we need to do to improve this power factor. Okay, so I just cleaned things up here by redrawing the power triangle, so we got rid of a little bit of clutter here. Remember, this is our P value in watts of real power. That's coming from our resistive branch. Here's our net reactive power, which is QL net, 1683.36, and our S value for our original power triangle without correction. Notice how if we go about determining our power factor, which cos theta or P over S, our power, real power over our apparent power, 1440 over 2215, I come up with a 0.65 power factor. So how do we go about improving this such that we can bring this to a 0.9? So what we're going to say is we desire a PF of 0.9. We're not bringing it to unity. We want to bring it to 0.9. So what does that mean? Well, that means in our new power triangle, we'll be adding a value of QC in here that's going to bring this S value to one that is equal to a 0.9 power factor. The thing is, in our new power triangle, what's the same? Well, our 2215 isn't the same. No doubt, that's our whole purpose. We're bringing our VA value down to a value smaller, which is going to draw less current from that source. So VAs isn't going to be the same. The angle isn't going to be the same. And the VARs aren't going to be the same. But certainly our real power won't change. We're going to have still be working with a 1440 watts of real power. So how do we come about working with this? Well, we know PF, we know P, we're just looking for S, right? So what do? We can go S equals P divided by PF. So that's going to be 1440 watts divided by a 0.9 power factor. That's our desired power factor. So now I can go 1440 divided by 0.9. That's going to tell me that my S is going to be 1600 VA. Right? So I'm looking for 1600 VA here, and now I can essentially draw a new power triangle that's going to be 1600 VA at an angle corresponding to 0.9, right? So I'm going to look at power triangle, maybe something like this. We're just going to figure out this angle for 0.9. So how are we going to figure out the angle? It's going to be cos, it's going to be the arc cos of 0.9. So the arc cos of 0.9 is indicating 25.84 degrees. So 25.84 degrees. You see where we're going with this? That means that this is 25.84 degrees. And what do we know this is? 1600 VA. So then from there, we can just do a polar to rectangular conversion, and we can figure out what our total value of QL will be, right? So let's do that. So if we do 1600 at angle 25.84, then we can look at our horizontal and vertical components of that, or essentially our real and imaginary power. And so if I just scroll over to the QL value in that power triangle, it's going to be this, 697.38 var. So that's our total amount of QL now that's going to be in our power triangle once we correct to 0.9. Here's the thing though, in our original circuit, what did we have for total var? 1683.36. We're bringing it down there, and how do we bring it down? By adding QC. So we got to figure out the value of QC required to do that. So we just subtract 697.38 from 1683.36. So 1683.36 is our original var. we want to subtract 697.38. So we'll do that, 1683.38 minus 697.38. And I'm just going to round this off to 986 bar for the purposes of this demonstration. So 986 bar is what we need for a QC value, right? So that means QC equals 986 bar. And our QC is going to be determined by V squared over XC. So our XC value can be determined by V squared over QC. So let's figure out what our XC would be. 120 squared divided by 986 gives us 14.6, yeah, 14.6 ohms. So that means that we need to add a correction capacitor in here. If we want to bring it to 0.9, the correction capacitor is going to bring it to 0.9. It's going to have an XC value of 14.6 ohms. Okay. Now you might want to slow this whole presentation down by pausing the video and stop here and there. But essentially, remember what we're doing is we're bringing in QC as a capacitive branch in order to drop what was originally 16.83 of net inductive power down to 697.38 net inductive power. That's going to improve it to a 0.9. So we worked our way through the process. We said it has to be an XC value of that. Now, using 60 hertz, all we have to do is determine the actual C value. So C is going to equal 1 over omega XC. So 377 is our omega for 60 hertz, so let's figure that out. 1 divided by 377 times 14.6. Answer is going to be in microfarads. We're going to list this in microfarads based on the decimal places we have here. And it looks like it's it's 181.68 microfarads. So that's the amount of capacitance we would want to add in this branch in order to bring this to a 0.9 power factor. Okay? So what I'm going to do is just bring up this circuit in multisim, and then I can demonstrate power factor and things like that when it comes to this circuit. So that's what I'll do next, and I'll edit it and splice it into this video. Okay. Okay, here is a circuit I built in multisim. This isn't the one that we covered on the whiteboard here previously, and I'll bring that one up in a minute. I just wanted to look at this circuit with respect to current, right? And so first of all, what we're going to do is we're going to look at the circuit as an RL parallel circuit that needs correction, or that you could pursue correction on. And what I wanted to do was, first of all, look at the currents that would make up this current triangle, and how here's the total current of 15.6 amps being measured by this XMM1 as your total current AC ammeter. And then we're looking at XMM2 of 12 amps for the resistive branch, which of course is 120 divided by 10. Then you have your 32 millihenry inductor here, of which you've got 9.947 amps of branch current. And then of course this XMM5, which is measuring the branch 2, or the inductive branch, and the capacitive branch current, is going to be the sum of those two currents. Now, of course, with the switch open, as you can see, XMM4 for the capacitor branch is showing 0 amps, of course, like it should be. So that means essentially you're looking at adding a 12 amps at 0 degrees to a 9.947 amps at minus 90 degrees, or a minus J component to the inductor current, of which the total current is your 15.587 amps, or 15.6 amps. This value of 120 times 15.6 would obviously give you your total VAs. Okay, so what we're going to look here, and now notice how I didn't put the correction capacitor right over here across the source. That doesn't mean it's any different than correcting it here. It's still right across the source, right across the load. But I wanted to do it in this way so I could demonstrate the net reactive current using this ammeter. So what I'm going to do next is just close that switch, and we're going to take a look at the currents now. Notice how now, with a value of 12 amps of total current and an IR branch of 12 amps, that tells us without a doubt that we're at unity. For a parallel circuit, when your total current equals your resistive branch, that tells you that you're at unity. And we can further prove that by taking a look at these two currents, right? IL equals IC. 9.947, 9.948. Those two currents are equal. And so now we have a circuit operating at unity with IL equaling IC. Notice how here you've got the total current to these two branches as essentially 0. We've got microamps of current there, which we're going to call 0. So if we were to put a power analyzer on here and look at the power factor of this circuit, no doubt we would be looking at a power factor of 1, circuit phase angle of 0, your voltage and current would be in phase, and your S value, or your VA value, is going to equal your P value, or your true power. Okay, so what I wanted to do next was to take a look at this one. And in taking a look at this one, this is the circuit where we started before correction. And again, notice how I just showed the capacitor as the last branch here. I could even go in and change that just so that it's not confusing. Maybe I'll do that now. Okay, so what I did is I just changed the configuration so it was consistent with what we showed on the whiteboard there earlier. And so I've got my correction capacitor here with the switch in it, so we can compare the two power factors and the two real power values. Now notice how in this case we're seeing our 1440 watts, or our 1.44 kilowatts there, which is our power dissipated by our resistive load. That's real power. But notice how it's indicating that we don't have a VA value equal to that, because we're working at a power factor of 0.65. And when we first started the power triangle of this arrangement, if you remember, that's what we calculated. We calculated a 0.65 power factor. When we now turn on the correction capacitor, it's going to change the power factor, but of course the real power will be staying the same because this is a watt meter. But no doubt the total current will drop. So the total current will drop from what it is at a 0.65 power factor to a value of total current that's consistent with 0.9. Because remember, we were correcting this to 0.9. We didn't take it all the way to unity. Okay, so here's the watt meter, and it's indicating that we have a 0.65 power factor. So if I go in and actually close this switch to bring in the correction, and notice that's the value we calculated of 181.68 microfarads, and then we just look at the corrected circuit. Notice how here we have the same amount of real power, average power, true power, because of course that's not going to change, but our power factor is now at 0.9.
And so what that means is that certainly we have less total current flowing in this circuit because we've added that capacitive branch to take away from that QL value, and we see a 0.9 value here. Now this was the same values and everything that we just did in our calculations, and now we're verifying it using multisim here. So yeah, okay, I just wanted to do this presentation with regards to parallel power factor correction, and I think that should conclude that. So you know, if you haven't done it already, go into your RLC parallel circuit quiz and complete everything that's there. But be aware that in the RLC parallel circuit quiz, the values change every question. So there's not a progressive kind of thing like it was in series. The values change every question. Okay, good luck everyone.